congruence theorem proof is going to follow the same kind of general theme, or the same general format. We have three boxes, and all of these three boxes together lead us to the third box, or, sorry, the fourth box. So these three boxes, let's call them box 1, 2, and 3, they all funnel into box number 4. And here's why. So all of these theorems, so for example, if we have side, 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 then we can prove that the triangles are congruent. So what that means is we need to prove each pair of sides are congruent. So we have in box 1, this would be one pair of sides. In box 2, and also in box 3, we have a different pair of sides. And what that allows us to do then is it allows us to prove that the triangles themselves are congruent. So let's say triangle something or other, I don't know its name yet, will be congruent to triangle some other thing. So that's why we're always going to have this three boxes kind of flowing into one. So let's begin our first proof. Let's give it a shot. Oh, I forgot about one thing. Sometimes there are things from diagrams or just how these pictures are drawn that we can consider as kind of given information. So when we have two triangles that share a side, then we can use that shared side in our proof. So for example, triangle side length AB and BA would be congruent to itself. And then also we have the sort of this bow tie type shape. Whenever we have two lines intersect, then we create these vertical angles. So in this case, vertical angles 1 and 2 would be congruent. And that doesn't need to be specifically given to us, but it's sort of one of those pieces from the diagram. It can be assumed given to us. Now we're ready to start some proofs. So first example is we want to prove that these two triangles are congruent. First off, let's figure out which triangles we're talking about. So let's name them. Now, as you remember from other videos, naming triangles in order to prove that they're congruent is an important thing. It's important to keep the order correct. So let's take a look at this triangle on the left. Maybe we could start at angle T here. If we follow T and kind of head in the direction of I, end up at C. So we could say triangle TIC. Well, what is angle T, this angle up top here, what does that correspond with? Well, in this other triangle off to the right, that angle is made up of the shared side and also the segment with one congruence mark. So the angle that shares one congruence mark and fits the shared side is this angle. So we'll begin naming our second triangle with C. In triangle TIC, we follow T towards I, end up at C. In other words, we go down the segment with one tick mark and follow the segment with two tick marks. In the green triangle, the one off to the right, we're going to follow one tick mark, head towards these second congruence tick marks. So triangle C is where we'll start, head toward A, end up at T. Oh, I can't spell apparently. CAT. So we want to prove that triangles CAT and TIC are congruent. How are we going to do that? Well, let's take a look at those congruence marks again. I see I've got one pair of segments. Let's call this IC. IC and AT must be congruent because they both have these two pairs of congruence marks on them. And likewise, this segment TI is going to be congruent to segment AC. And then finally, just from the way that these two triangles are drawn, we've got a shared side up the middle. And so what that means is I've got the green pair of sides, I've got the blue shared side up the middle, and I've got the red pair of shared sides. So we're going to prove that these two triangles are congruent using side, side, side. So let's get to it. So first off, remember we were trying to prove that triangle TIC was congruent with triangle CAT. We were given the two green sides are congruent, So that's TI and CA. And then also we have the two red sides are congruent. So we've got what we have given, we have what we're trying to prove. Now let's start filling in our three boxes. In the previous slide, we established that we are going to use the side-side-side congruence theorem for this proof. So we can fill that in as the reason right now. Let's see, if. And so in order to prove that these two triangles are congruent, well, first off, we should name them. We wanted to prove that triangle TIC was congruent to triangle CAT. In order to do that, we need to first prove that we've got a pair of sides, another pair of sides, and a final pair of sides that are congruent. The reason we need to do that is in this triangle congruence theorem, we have the if part of the sentence, the hypothesis, and that must be satisfied in order for the conclusion to be true. So which pair of sides do we have? I know AT is congruent to IC, and the reason that I know that to be true is that's given information. Likewise, the green segment TI and CA are congruent for the same reasons. We've got given information. And then lastly, we need to talk about the shared side. So that shared side is kind of strange. In triangle TIC, I see that the segment is, if we follow the order of the letters, then the segment would be called TC. However, the corresponding segments in triangle CAT would be, instead of TC, it would actually be CT. And that follows from the order of the letters in the names of the triangles. So we have that shared side, and we need to talk about the fact that that shared side gives us congruent segments. So TC is shared by both triangles, and as a result, it must be congruent in both triangles. And the statement that we use is called the reflexive property of equality. And now we're done. Each of our different puzzle pieces has fallen into place. We've proven what it is we're trying to prove, and now we're good to go. Proof number one, done. Let's take a look at this next one. Again, we're dealing with two triangles that we want to prove congruent, so let's name them. So we can call them triangle TON and triangle FUN, as in proof is a ton of fun. All right, so we want to first prove, all right, TF and OU bisect each other. What does that mean? Well, this word bisect. Bisect means cut in half. So TF and OU cut each other in half. In other words, TF refers to that long segment. TF is cut into two equal parts. Similarly, OU is cut into two equal parts. So now we have two pairs of sides. We've got the reds and the blues. We've got side and side. And right now we're missing a piece, right? We could either use side, 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 side angle, side. And so we're missing a piece. But the way that the shape is drawn, we've got these vertical angles. And vertical angles are always congruent. And so therefore, we're going to prove that these two triangles are congruent using the side angle side theorem. So let's get started. So we know what it is we want to prove. We want to prove that triangles TON and FUN are congruent. And we agreed we're going to use the side angle side congruence theorem. So we can talk about a pair of sides that are congruent, a pair of angles that are congruent, and another pair of sides that are congruent in each of those boxes. So let's start with the reds. I know that UN and ON are congruent. Next, the other pair of sides, the blues, those blue sides are congruent. And finally, the angles up the middle, angle TNO and FNU. Well, okay, so why are all of these segments congruent? The red segments, UN and ON, why are they congruent? Well, they're congruent because TF and OU bisect each other. And what that means is, I know that TF bisects OU. Also, OU bisects TF. So for the red segments to be congruent, which segment is doing the bisecting and which is being bisected? That's an important question. In this case, TF is doing the bisecting and OU is being bisected. The opposite is true for the blue segments, TN and FN. In that case, OU is doing the bisecting and TF is being bisected. Now, the connector reason, you have to ask yourself, what does bisect mean? Well, bisect means cuts in half. And so for each of these reasons, we're going to use the segment bisector definition. And lastly, we need to talk about where those green angles came from. The green angles came from the vertical angles, and always vertical angles are congruent. So we need a box that says, hey, I have vertical angles, and then the box below it can say that they're congruent. So there's the statement, TNO, FNU are vertical angles, and as a result, vertical angles are congruent. So the statement is, if we have vertical angles, then those angles, those vertical angles, are congruent. Super. We're done. This shape kind of looks similar to the first proof that we dealt with. We've got two triangles and they share a side length. However, the given information is different. We've got these segments, let's call it MA and HT. Those segments are parallel, right? That's what that little arrow means. And parallel lines always, always, always give us angles. So these parallel lines are cut by a transversal to give us these two angles. So those two angles are congruent. Now, furthermore, these segments have these congruent tick marks on them. And as a result, MA and HT are also congruent. So they're both congruent and they're also parallel. And then finally, we've got a shared side up the middle, segment AT. And I know those segments are always congruent to themselves. So we can prove that these two triangles are congruent using the side angle side theorem. Right, we've got the green side length, the red angles, and the blue shared sides. So we're dealing with side, angle, side. So let's piece this together. First, we know MA is parallel to HT, and we also know that MA is congruent to HT. All right, so let's talk about those green sides. We know MA and HT are congruent, and that's given information. Next, we want to talk about the two red angles that we had. We had angle MAT and angle HTA. But why is that true? Well, that's true because of this given information, the two parallel lines. So we have to mention that fact. So the fact that MA is parallel to HT, if we have parallel lines, then alternate interior angles are congruent. So I know it's a bit abbreviated, but that reason, right, the connector with the arrow says if parallel lines, then alternate interior angles are congruent. And then finally, we have the blue sides. We have segment AT, and it's a shared segment. And shared segments are always congruent. Now, we're not quite finished with this proof. Yeah, we've proven that the two triangles are congruent, MAT and HTA, but that's not exactly what we're trying to prove. We want to prove that angles M and H are congruent. In other words, we want to prove that these angles are congruent, H and M. Well, in order to do that, we're going to use the CP-CTC. See, once we've established that the two triangles are congruent, then all of the parts of the two triangles are congruent. That's what CP-CTC stands for. Corresponding parts of congruent triangles are also congruent. And so we can say, given the fact that triangle MAT is congruent to HTA, that means angle M must be congruent to angle H. And now we're done with the proof. This last proof is dealing with something similar to what we've seen before, but in a slightly different way. Here we've got a bisector. However, it's not a segment bisector, it's an angle bisector. I see AN bisects angle FAC. Well, here's angle FAC, and AN cuts it in half. And so that means that these angles will be congruent. Furthermore, we've got these congruence marks, and so that means we've got segment FA and segment CA are congruent. And lastly, there's that shared segment, AN. And so it's getting kind of busy in there, but we've got a pair of sides, the blue shared side. We've got a pair of angles that come from the angle bisector, and then the green sides, FA and CA. So we can prove that these two triangles are congruent using side angle side. So let's get to it. So we're given that AN bisects FAC, and that gave us that these two angles were congruent. Use green. We also had the shared segment, and then also these congruence marks tell me that FA and CA are congruent. So in the previous slide, we agreed we were going to use side angle side to prove that the triangles were congruent. So SAS. And we have, let's see, we've got the red sides that we just mentioned. There's the green angles that come from the angle bisector. And lastly, the shared side. Hopefully this stuff is starting to look familiar to you now. So the red sides, that was FA and CA. And from those congruence marks on the drawing, that's just given information for us. The angles, the green angles, let's call them angle FAN and CAN. The fact that those two angles are congruent was established from this given piece of information. Right? AN bisects angle FAC. And what does bisect mean? It means cut in half. So we need that as a statement. And then just like in a previous proof, the reason that we're going to use to make that leap is essentially the definition on a bisector. However, this one is slightly different. In previous proofs, we had the segment bisector definition. Well, we're bisecting an angle this time. So what does it mean to bisect an angle according to the angle bisector definition? And then that shared side is starting to look familiar to us, hopefully. And then, lastly, let's make sure that we proved what it is we're trying to prove. We wanted to prove that segments FN and NC, in other words, these little segments, are congruent, which we can prove using the CP-CTC. So here we have established that the two triangles themselves are congruent, and so therefore all of their parts will be congruent as well. And we mentioned that before, that's the CP-CTC. Or if you'd rather, the CP-CTC is a conditional statement. If you'd rather say, if the triangles are congruent, then all the parts are congruent. So if the triangles are congruent, then all the corresponding parts are congruent. So the blue statement is a little bit longer. That's why we can use the CP-CTC as an abbreviation of that statement. So we're given that WT bisects NP, and we want to prove that these two triangles are congruent. So first things first, we need to name the triangles. So if I start with angle N here as one of the sides in my triangle, the corresponding angle, well, in this second triangle, we have a choice. It's either going to be T or it's going to be P, and how will we know? Well, angle N is created by this long parallel side and then this long side connecting to E. And likewise, angle P is made from this parallel side and the long side connecting to E. So N corresponds with P. And from there, we can kind of piece together the rest. If we go from N to E and end up at W, then again, we can start at P, head toward E, end up at T. So please also note that we have these arrows on segment PT, on segment PT and on segment NW, and those arrows indicate parallel lines. So that's other given information. NW is parallel to PT. So how are we going to go about proving this? We need to prove that these two triangles are congruent, and, well, we're missing some stuff. Right? We can prove triangles are congruent using SSS, SAS, ASA, and AAS. And right now we have no sides congruent and no angles congruent. So let's piece a few things together. Let's take a look at this given statement, the fact that WT bisects NP. So WT is doing the bisecting, but NP is being bisected. NP refers to this long segment, and we know that that segment is bisected, or in other words, it's cut into two equal parts, and WT is doing that cutting. Secondly, we have these parallel lines, and parallel lines, well, if we consider these parallel lines cut by the red transversal, then angle P and angle N would be considered alternate interior angles. And then finally, the way that these two triangles are drawn, we have intersecting lines, or intersecting line segments, and intersecting line segments create vertical angles. So we've got the blue angles, the red segments, and the green angles means that we can prove using the ASA theorem. So let's get to it. Let's write our proof. So right away, we know that the given statements, well, the given statements are there, but the proof statement, that's what we're trying to prove, so that goes in that last box down here. And in the previous slide, we ascertained that we're going to use the ASA theorem to prove that. And so we need to talk about which pair of angles, which pair of sides, and which pair of angles are congruent in order to prove that the triangles are congruent. Well, we've established that angle N is congruent to angle P. And the reason why is we had those parallel lines, NW and PT. Next, we need to talk about the segments that we had congruent. We knew that NE and PE were congruent. And that came from the fact that WT bisects NP. And then finally, we had our vertical angles. And those come from the fact that, well, we have intersecting lines because of the way that this particular figure is drawn. So those vertical angles are always congruent, which means angle NEW is congruent to angle PET. And so there's our proof. We're done. Just scroll down a little bit so you can see everything. So, by the way, with this particular proof, there's another way to go about proving it. And that proof, a second way of proving it does not use these vertical angles. And so all of this blue information we actually wouldn't use. And so instead of the blue angles at NEW and PET, we can still use the fact that NW and PT are parallel, right, these segments. And that tells me that alternate interior angles are congruent. Well, angle W and angle T are also alternate interior angles. So we could use that information for the proof as well. Though the difference is, instead of using ASA, we would be using AAS. And here's why. In AAS, the pair of sides, I guess, that are congruent are the non-included sides. And so if we just consider triangle NEW, let me pull that out for a second. If we just consider triangle NEW, we know that these segments are going to be used, or that segment, I guess, this angle and this angle. Those are the used segments and the used angles in that proof. And you'll notice that the red segment is only connected to one of the angles. Right? It's only connected directly to that angle N. So we'll be using AAS. So let's do a little bit of rearranging of our proof. So since we're dealing with an angle side proof, we'll have to talk about one pair of angles which is shown here, another pair of angles, and then that pair of sides that we've already established. Okay, so from the fact that NW is parallel to PT, that gave us this first pair of angles, that N and P were congruent. Now we also established that angle W was congruent to angle T. And the reason why is the exact same reason as N and P are congruent. It's the same pair of parallel lines, but different transversal. And so the fact that NW is parallel to PT also gives us angle W and angle T congruent. And so that gives us our proof, which is similar to the previous proof, slightly different. It's using the AAS instead of the ASA. So I guess we've just established there's more than one way to prove this particular statement. All right, next example. We're given that GO and LF are parallel, OL and GF are parallel, and our job is to prove that G and L are congruent angles. So the sub-step, or the step kind of before proving this is true, is we'll want to prove that the two triangles are congruent. So we're going to start by proving the triangles are congruent, and then we can use the CP-CTC, like we've seen before, to prove that angle G and angle L are congruent. So first off, let's kind of figure out what we have here. These segments are parallel, GO and LF, and that refers to GO and LF. Well, what of it? Well, with parallel lines, you should always be thinking about angles. And in particular, well, which pair of angles? Those yellow lines are parallel, and they are cut by this transversal, OF. So if we've got parallel lines here, cut by a transversal, we're thinking about angles. And in particular, the only angles that touch those yellow lines are angles 1 and 4. So GO parallel to LF, that gives us angle 1 congruent to angle 4. Next piece of given information is that OL is parallel to GF. OL refers to this segment, GF refers to this segment, and they're still cut by that red transversal. However, the angles that are congruent because of that fact are different. Angle 2 is created by a green line. Angle 3 is created by a green line. And so that means that angles 2 and 3 are congruent because OL is parallel to GF. So we've got two pairs of angles. The way that this particular image is drawn, we've got a shared segment, OL. And since we have two pairs of angles, we can either use AAS or ASA. Oh, ASA. But which one is right for us? Well, we've got to think about the included side. If you just consider triangle GOF, I'll just recreate it down here, GOF. So that's this triangle in here. Oh. That triangle. So if we just look at that triangle, we've got angle 1 up top here. We've got angle 3 down below here. And then we have that shared segment right in the middle. And so this follows angle, side, included side, angle. So we must use the ASA theorem and can't use AAS. So let's get to it. Let's write the proof. All right, so earlier we talked about using the two triangles congruent as a sub-step along the way. So we want to use the fact that GOF and LFO are congruent first. And however, the proof itself, remember, asked us to prove that angles G and L are congruent. And so once we've established that the two triangles themselves are congruent, we can use the CP-CTC to say that angles G and L are congruent. All right, so now let's get back to the bulk of the proof up above. We need to talk about a pair of angles, a pair of sides, and another pair of angles. From the given information, we know GO, and LF are parallel, which meant angles 1 and 4 were congruent. Similarly, because OL is parallel to GF, angles 2 and angle 3 are congruent. And then lastly, OF is a shared segment in both triangles, and as a result, it'd be congruent in both GOF and LFO. So now our proof is done. Scroll through it so you can take a look at the final proof. It kind of looks like a 6, doesn't it? It should be a G. All right, here we have our final example for the day. We've got a goal of proving that MN and EA are congruent. Now, in order to do that, we're going to have to prove that the two triangles are congruent. So those two triangles, let's name them. So once again, proving that these triangles are congruent is going to be kind of a sub-goal in order to prove that these segments are congruent using the CP-CTC. So let's piece this together. Which of our triangle congruence theorems can we use? We know that MN is parallel to EA. So MN and EA are parallel. And what that tells me is any angles that are created by those segments will be congruent, either congruent or supplementary. So if we consider MN and EA, and they're cut by that transversal, then the angles that created them, sorry, not that created them, but the angles that are created, if we look down at these angles, we've got angle 2 and angle M would be considered corresponding angles. So those are congruent. So that fact tells me that angle 2 is congruent to angle M. We have given information that N is congruent to A, so this angle and that angle are congruent. And then lastly, E is the midpoint of MG. Well, what does midpoint mean? Midpoint is the middle point. So here's MG, and E is right in the middle. In other words, that segment, ME, has to be congruent to EG. So now, in these triangles, let's just pull out one of those triangles. In these triangles, we are given that these blue angles are congruent. So that's angle M and angle 2. We're given that these green angles are congruent, angle N, angle A. And then finally, we've got that midpoint segment, or that midpoint of a segment, which means that these segments are congruent. So we've got the green, the blue, and the red. We can either talk about angle, angle, side, or angle, side, angle. And how do we pick? Well, in angle, side, angle, the side must be the included side. In this triangle, this side with the red tick marks is not the included side because it only touches that blue angle. It has nothing to do with this green angle over here. So as a result, we're not going to use angle, side, angle. We must use angle, angle, side in order to prove that the triangles are congruent. So let's get started. We know since we're proving that segments are congruent, we must first prove that the triangles are congruent. And then once we know all the triangles are congruent, from that information, we can then prove what it is we're trying to prove, specifically that MN is congruent to EA. So hopefully these last two steps, let's call this like step 1, step 2, hopefully these last two steps are looking familiar to you. First, proving that the triangles are congruent, and then second, using that congruence to prove that the segments or the angles or some parts of the triangles are congruent. All right, now since we're using the angle side theorem, we need to talk about which pair of angles, which pair of other angles, and then which pair of sides are congruent. Well, let's we can just start in order of the given information. We know that MN is parallel to EA. So MN is parallel to EA, and we saw that that gave us these corresponding angles are congruent. So angle 2 and angle M are congruent. So parallel lines make corresponding angles congruent. Next, we can take a look at the next piece of given information. Says angle N and angle A are congruent. And so that can go in our next box. And we need no statement above that box because that was given information. So we don't need to explain why it is because, well, that's just given to us. And then finally, the segments. We knew that ME and EG were congruent. And the reason was E is the midpoint of MG. And midpoint means midpoint, middle point. It's splitting up the segment into two equal parts. And so that midpoint definition will give us that information. All right, and now I think we're done with this proof. All of our given information is used up. Here we've got the green is used, the blue is used, and the red is used. And we've proven first that the triangles are congruent, and then using the CPCTC that the segments are congruent. So we're all done.